Going to talk about alternating series. So alternating series meaning the terms in the sequence alternate in sign. So for example, the alternating harmonic series would be this: 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, and so on. And the way you get a series to alternate is you use this little technique, -1 to the n minus 1 power or to the n power, depending on which terms you want to be negative. If you want the first, third, fifth, aka odd terms to be negative, you would do -1 to the n. If you want the even terms to be negative, you could do -1 to the n minus 1. Oh, is it not? Okay. So here's how to determine whether an alternating series converges or diverges. We use this thing called the alternating series test. First, you need to know, one, that the series is decreasing, so b sub n plus 1 is less than or equal to b sub n for all n. And two, that the limit of the sequence b sub n is 0. Then we can say that the series is convergent. All right, and we're going to prove this one. All right, so to prove this, we're going to look at the even partial sum. So if I look at S2, that's just the sum of the first two terms. So that's just B1 minus B2. And we know that that has to be positive because this is satisfied. This first condition says that basically the absolute value of the terms will decrease, right? And then I can say S4 is just S2, so the second partial sum, plus B3 minus B4, right? And because this is positive, again, because of this condition, we know that this has to be bigger than S2. The second partial sum, because you're adding a positive number onto S2, right? And so we can say that the even partial sums are increasing, meaning S4 is going to be bigger than S2, but smaller than S6, which is going to be smaller than S8, and so on. And I can also say that the nth even partial sum, so S sub 2n, is just B1 minus B2 minus B3 minus B4 minus B5, and so on. And since each one of these is positive, we're basically taking a bunch of values away from B1, right? meaning the nth partial sum has to be less than B1. All right, so here's what we've shown. The sequence of partial sums S sub 2n is bounded. We showed that it's bounded both by 0 and by B1. And monotonic. Do you guys remember what monotonic means? It means either always increasing or always decreasing. And we had a theorem that said that if you have a sequence that's bounded and monotonic, it has to converge. So I'll say thus convergent. What does it converge to? Who knows? Let's call it S. So let's say the limit as n approaches infinity of S2n converges to S. So now we've shown that the even partial sums converge to some number S. What about the odd partial sums? Well, I would just want to look at the limit as n approaches infinity of S sub 2n plus 1. So that would be the odd partial sums, right? Well, an odd partial sum is just an even partial sum plus one more term, right? Like think of S3. S3 is just B1 plus B2 plus B3. It's just the sum of the first three terms, right? So isn't S3 just, S3 is S2 plus B3? Meaning the second partial sum, which is just the sum of the first two terms, plus the third term, right? Does that logic make sense? Have I lost anybody? Okay. So then S sub 2n plus 1, isn't that just that's just S sub 2n plus one more term, which would be B sub 2n plus 1. So this is just the odd terms in the sequence. All right, well, we already know this limit. What's the limit as n approaches infinity of S sub 2n? Yeah, we already proved that that's convergent. We said that it converges to S, right? So that limit just comes out to S. Now let's think about what do the odd terms have to do as n approaches infinity? Well, if we look at our conditions up here, it says the corresponding sequence has to approach 0, right? That's our second condition. So that means the limit as n approaches infinity of B sub 2n plus 1, also, that's going to have to go to 0. I mean, if all the terms approach 0, then the odd terms have to approach 0 as well, right? So I get S plus 0, which is S. Good, so now I've shown that the even partial sums go to S and the odd partial sums go to S, meaning the overall series has to converge to S, right? So that's it. We've proven that the series will converge to S if these two conditions are true. All right, so let's use this. This is sort of a visual proof if you think about the partial sums on a number line. So you got your first term, and then you add your second term, and that's a negative number. That's going to get you back. And then your third term, that's another positive number added to it, so it brings you more to the right. And then your fourth term, and basically you're just going to keep adding terms, but it's alternating, right? One's positive, one's negative, and they're eventually going to converge on the overall sum S. All right. Now we know the harmonic series by itself is divergent. What about the alternating harmonic series? So that is the sum -1 to the n minus 1 over n. So all we want to do is use the alternating series test, which is just these couple conditions that we need to check on, right? We need to check that the corresponding sequence is decreasing and that the limit as n approaches infinity for that sequence is 0. Notice, this is the absolute value. This is just b sub n. This is not the actual alternating. All of these are positive is what I'm saying. We want to look at the sequence as a positive sequence. So the corresponding sequence for us here is just 1 over n. So b sub n is just 1 over n. So condition 1, I need b sub n plus 1 to be greater than, or I'm sorry, less than or equal to b sub n. So can we show that here? 1 over n plus 1 is less than or equal to 1 over n. Is that true? And if it's not immediately true, you can just do some algebra. In this case, I could cross multiply, and I would get that n is less than or equal to n plus 1, and that is definitely true, right? All right, condition 2. I need to show that the limit as n approaches infinity of b sub n is 0. So for us, that's just the limit as n approaches infinity of 1 over n, which is definitely 0. And then we'll just say, okay, both conditions are satisfied, therefore sigma -1 to the n minus 1 over n converges by the alternating series test. And that's it. As long as it's an alternating series and both those conditions are satisfied, then we've proven it convergent. All right, let's look at this example. All right, this is an alternating series because of this -1 to the n. But if we let b sub n just equal the sequence without that alternating portion, so 3n over 4n minus 1, and I look at the limit as n goes to infinity, that's going to be, I'm going to divide everything by n, so I'm going to get 3 over 4 minus 1 over n. That comes out to 3/4, which is not 0. So my condition for the alternating series test is not satisfied. Now, this does not say, it does not say that if these conditions aren't satisfied, it's divergent. It says that if these conditions are satisfied, it's convergent, right? So all we've shown is that one of these conditions, this one, is not satisfied. So that doesn't really tell us anything. It still could be convergent or divergent. But if we just look at the limit as n approaches infinity of the original sequence, -1 to the n times 3n over 4n minus 1, that won't exist because the sign will continue to alternate. The -1 just makes this continue to alternate, so it's not going to approach anything. I mean, if you like, it will approach 3/4, but also it will approach -3/4, right? So overall, the limit doesn't exist because it's not approaching a single number. It's like kind of bouncing back and forth, approaching +3/4 and -3/4. So this does not exist. Do you guys remember the test? There was a test that said, it was the first test we learned actually, that said if the corresponding sequence doesn't go to 0, then the series diverges. And that's just called divergent by, and this was just called the test for divergence. So we tried to use the alternating series test. The conditions weren't satisfied, so then we kind of had to default to a different test to prove divergence. Okay. All right, let's do one more. Test this series for convergence or divergence. All right, so let B sub n equal the sequence, but without the alternating part. So just the n squared over n cubed plus 1. So first condition, I need to show that it's decreasing. Now, it's not immediately obvious that this is decreasing. So I'm going to let f of x, I'm going to turn it into a function equal x squared over x cubed plus 1. And if it's not immediately clear that it's a decreasing function, you have to actually prove it. What tells us about if a function increases or decreases? That's true, but I'm talking calculus. Think back to last year. How can you tell if a function is increasing or decreasing? Its derivative. If its derivative is negative, it's decreasing. If its derivative is positive, it's increasing, right? So let's take the derivative here, f prime. I mean, you could, it just won't be obvious. So if we did that, we would have n plus 1 squared over n plus 1 cubed plus 1, and then you'd have to compare that to just the original n squared over n cubed plus 1, and is that immediately clear that one is greater than or less than the other? Not necessarily. So we're just going to use calculus to show, and in fact, this doesn't immediately decrease, it just decreases eventually. We'll see. All right, so you guys remember quotient rule? Low, which would be 2x minus x squared. This is going to be 3x squared plus 1. Nope. Yes. No, 3x squared. Sorry. Over x to the 4th. No. What's wrong with me? X cubed plus 1 quantity squared. All right, so let's simplify that. I can factor what? Factor out an x. What would I be left with? 2x cubed plus 2 minus 3x cubed. So that's 2 minus x cubed over x cubed plus 1 squared. All right, so we're going to set this equal to 0 and we're going to solve, because what we want to know is where the derivative is positive or negative. I can just multiply out the denominator, that's gone. And I'm left with x times 2 minus x cubed equals 0. So that gets me x equals 0, or the cube root of 2. And so what I want us to do, for us, we don't care about the 0, because x is replacing n for us in this case, and n is always positive, right? I don't really care what's going on to the left of 0, but I do care what's going on around the cube root of 2. So I want to know, where is f prime positive versus negative? All right, so we'll test a number. What's less than the cube root of 2? 1 has to be less than that, right? What's the cube root of 1? 1. So the cube root of 2 has to be more than 1, right? All right, so 1, if I plug in a 1 to f prime, do I get back a positive or a negative? So what would we have? We would have 1, 1, 1. So you'd have 1 times 2 minus 1. That's positive. So f prime is positive there, meaning f is doing what? Increasing. And then I can plug in like 2. If you plug in 2, you can see just from this term alone, that's 2 minus 8, right? So it's going to be negative. So that means that f is decreasing. So what we've proven, therefore, b sub n decreases after the cube root of 2, so after the first term, right? All right, so finally we've satisfied that first condition. Good. So the second condition, we just want to show that the limit as n approaches infinity of b sub n is 0. All right, so for us, that's the limit as n approaches infinity of n squared over n cubed plus 1. What am I going to divide everything by? Largest exponent in the denominator. So n cubed, right? So in the numerator, that's going to give me 1 over n. In the denominator, that's going to give me 1 plus 1 over n cubed. The 1 over n will go to 0. The 1 over n cubed will go to 0. That means I end up with 0 over 1 plus 0, which is 0. Both conditions are satisfied, so I can say, therefore, sigma -1 to the n plus 1 times n squared over n cubed plus 1 converges by the alternating series